going to look at relative extrema. Now I do have to say that in the in the first video for 13.1, uh, or the first example, there actually was a typo. So originally your equation in the previous section said negative x cubed minus 2x squared plus 15x plus 10. That when we were trying to find the derivative, for some reason in my mind, I'm thinking 3 times 2. So it's going to be negative 3x squared minus 4x plus 15. Uh, Now, in that case, what that means is that, you know, you had to figure out a way on how to factor this. So, like the way of which that you can factor this is by saying, for example, that you have that this is going to be negative times 3x squared plus 4x minus 15. And then from here, that's where you would say, like, you get negative 45 when you multiply those two. So you just have to think of um, two factors that you can use to break down into 4x or 4. So that would be 5 and let me see, 5 and 9, but this would have to probably be negative. So that gives you negative, and then you have 3x squared plus 9x, and then you have minus 5x minus 15, and this is where it gets kind of weird. You end up with negative, and then you have 3x multiplied by um, x plus 3, and then you have minus 5 multiplied by x plus 3. And you have that this simplifies even further to negative 3x minus 5, and then you have x plus 3. So that tells you that this actually simplifies a little nicely in the sense of derivatives. So this would give us that the values would actually be x equals to 5 thirds and negative 3. And then from there, you would just set up your interval line test, looking at the critical points. Well, we don't call them critical points just yet, but that's what they are. So you end up with negative 3, and then you get 5 thirds. So like you could plug in values such as like 0, and then maybe like 2, and then maybe like negative 4. Now notice that, for instance, that if you plug in negative 4, that's all going to be negative, but that's going to be positive. So that's going to be basically negative. So you have that that's going to be negative. And then if you plug in 0, you get that that's going to be positive. But if you plug in 2, well, if you plug in 2, you basically have 6 minus 5, and then that's all going to be negative. So you have that's going to be negative. So that means that the equation looks something like this. Now, if you plug these values back into the calculator, basically you're going to find that you'll end up with negative 3 comma negative 26, and you end up with the fractional point, like 5 thirds comma, believe it's going to be 670 over 27. Okay, so this will actually rectify what we had in the previous example in the other section. Now, I found that this is going to be a min and that this is going to be a max based on the behavior, because you have that this is a min and this right here is a maximum. So the question really becomes, how do I know what a minimum is and what a maximum is? So like, for example, if I go ahead and I draw, like, for example, like a function of which maybe it looks something like this. Well, basically I know that, for example, that from negative infinity to this point right here, that that's going to be increasing because of the slope of the tangent. But from here to here, I have that the slope of the tangent is going to be decreasing, so it's going to be negative. And then furthermore, I have that it increases, so it's going to be positive. So in that sense, I know that, if I have a function, that this is going to be my min and this is going to be my max, which you can see that there's these little horizontal tangents right here and right here. Okay, but the question is, like, how do we find those? So the chapter that we're working on right now, it's more or less the same. So let's say that we want to find all relative extrema. Okay, so let's say that we have the equation y equals x cubed plus 3x squared minus 9x plus 4. So to do this problem, we would have to find the derivative first. So that's going to be 3x squared plus 6x minus 9. Now, this actually factors as 3 times x squared plus 2x minus 3, but this factors even more as 3 times x plus 3 multiplied by x minus 1. So this gives us basically that you have that it's constant at negative 3 and at 1. So when I set it equal to 0, I have that those are going to be equal to 1 and negative 3. But we call these points the critical points. That's where the derivative is equal to 0. So what we do next is we just set up an interval line test. So when we set up the interval line test, we have that we're just looking at what the sign is. So negative 3 and 1. So we just need test points. So maybe like 0, 2, and negative 4. But we're plugging this back into this equation, to the y prime. So if I plug in 0, I'm going to get that it's negative. If I plug in 2, I'm going to get that it's positive. If I plug in negative 4, well, I have 3 times negative. Um, okay, so negative, negative, negative 4. Yeah, that's going to be positive. So we have that that's going to be positive. Now what that means is that the behavior of the graph, or the characteristic to it, looks something like this. So what that means is that I already know that negative 3 is going to be a max and it's going to be a min. Now that means that basically all that you need to do is just plug in those values, negative 3 into x cubed and 1. I'm sorry, negative 3 into this equation and then 1 into this equation. So we can do that, but keep in mind that these functions or these values are not absolute. They're actually relative because the domain is all real numbers and the range is all real numbers. So in that case, there's never a largest max nor is there's a largest min. So it's just relative to that region. So we'll just go ahead and say, okay, well, we'll plug in 1 and we'll plug in negative 3. Okay, but we got to go back and figure out what that's going to be equal to. So 1 is basically just 1 plus 3 minus 9 plus 4, which is equal to, let's see, okay, so 1 plus 3 plus 4 is 8, so that's going to be negative 1. Now for 3, you have that that's going to be 27, negative 27. And then you have, that's going to be plus 27. This is really strange. Plus 27 plus 4. Okay, so that's going to be that. Okay, so this is going to be 31. Okay, now we go back and, you could have plugged that into your calculator, by the way. Okay, so we have -1, and this is what we call a relative min. Then we have 31, and this is what we call a relative max. Now, if we were to, say, for example, draw this graph, basically you would have that it would look a lot, let's say, like, for example, we'd go ahead and we draw it. Okay, so that's going to be our min, and we're going to have our max like way up here. So essentially we have, okay, so we'll just draw it a little bit better. And it is, okay, so that's a rough sketch of it. So we have that that's going to be 1, -1, and this is going to be -3, 31. So we can see that this is the min, and this is the max, but it's not the absolute. Absolutes will make more sense once we start to restrict our domains. Okay, now the other example that I wanted to look at um, is the following. Let's say that we have y. Okay, so we want to find the relative extrema for y equals to 1 over x squared plus 1. Now, this one's actually pretty special in the sense that this derivative is very easy. So we find y prime, and we can use quotient rule or reciprocal rule. So we have x squared plus 1 to the second power, and that's x squared plus 1 multiplied by the derivative of 1, but that's just 0, minus 2x multiplied by 1. So this equals to -2x divided by x squared plus 1 squared. Now notice that basically that if you set this equal to 0, it tells you that your critical point is equal to 0. So what that means is that you just do a test point of at 0, and what happens is that when it's going to be like -1 and 1, you'll notice that when you plug it back in that the denominator stays positive. So this is really just negative times negative, which is basically just positive. But then if I plug in 1, well, that's negative times a positive, which is just negative. So essentially we have the graph increases towards 0, but it decreases towards 0. Now I know that I said that I wasn't going to talk about like absolutes necessarily, but we're going to go ahead and talk about them because notice that if I take the limit as x approaches plus or minus infinity for 1 divided by x squared plus 1, that just goes to 0. That means that there's an asymptote at 0. So what that means is that 0, because it came up as a critical point of where there's a sign change, this is not only going to be a relative max, but it's also going to be an absolute max. Because if it has that the smallest value is 0, but the highest is at the point 0, which means that like the ordered pair that corresponds to that is 0, comma 1. So we're just going to call that the absolute max. But it's also the relative max as well. Um, and once we start talking more about absolute maxes, then it'll make more sense. But if you graph that equation in the x and y plane, well, you'll notice that basically it kind of looks like the bell curve. You'll notice that it goes like this. and then that's it. So we see that there is a horizontal tangent right here at the top where that's that point 0, comma 1. Okay, so we can see that this graph is increasing, but we can see that it decreases from 0 to infinity. So just be sure that you make those observations that, that it's increasing from negative infinity to 0, and then it's decreasing from 0 to infinity. Okay, now the last question or the last example that I'll show you is finding the relative extrema for y equals to negative x squared plus 4x. So we can do this easily because we know that basically if we take the derivative, we find negative 2x plus 4, and then that's basically it. Because the rest is just saying, well, negative 2x plus 4 equals to 0. So 2x equals to 4, but that means that x equals to 2. So that means that the point where you have critical values is at 2. So we can actually set up our interval line where we have that that's going to be 2, and then we can set up critical or test points like 3 and maybe like 1. So notice that y prime of negative 2 times 1 plus 4, that's going to be positive. So we know that it's positive. So that's positive. When we plug in 3, we have negative 2 times 3 plus 4, but that's negative. So we have that that's going to be negative. Now basically this is telling me that I have a max. And to be more specific, again, it happens to be a absolute max. And I know I keep on saying that I don't want to talk about it, but it keeps coming up, to be honest, for specific functions like x squared and the reciprocal function and so on. Now the thing that I need to find out though is what is that value 2? So y equals to negative 2 squared plus 4 times 2, but this gives me negative 4 plus 8, which is equal to 4. So that means that the maximum for that function is at 2 comma 4, and it's a relative max. However, I just said that it's an absolute as well. That's because if you look at the equation, um, if you graph it, if you graph y equals negative x squared plus 4x, you're basically going to find that it looks something like this. So this is at 2, and that's 4. And this right here, this is the value 2 comma 4. But you can see that basically that's the absolute also. Okay, now one thing to note is that when you're dealing with parabolas, this right here represents the vertex. So this is also known as the vertex of an equation, of a quadratic equation. Now, normally the vertex is found by taking negative b over 2a, comma, f of negative b over 2a. And that's actually a lot easier. Now, if you've taken like physics before, then most likely you have also a formula for calculating like the largest maximum for the height of a projectile. Um, but I mean, you can approach it using the calculus method too. And then of course, like, if you use your calculator, you can do that too by saying negative x squared plus 4x, graph it, go to second trace, and then go to the maximum. Choose a left bound and choose a right bound, and then just choose a guess. So see, 2 comma 4. So it's the same thing. But in any case, be sure that you use obviously like the first derivative to show that that the function is a maximum or a minimum in either case. Okay, so yeah, that's just the things that you'll need to remember in any case. That if you have a polynomial, you want to just make sure that you're accounting for every single every single horizontal tangent. So you have one right there, you have one right here, you have one right there, and you have one right there. So you would just have to figure out where these values are based on the first derivative. Okay, now let's see. You'll be able to basically use this information to figure out uh, what the sketch of the graph is without plugging into your calculator. So that's going to be the goals as you move on from this section. Okay, and the other thing of which that you'll need to look at is a little bit more of the applications, but not really much has changed. You're still looking at the cost, the revenue, and the profit. Okay, so in any case, like the idea is that you want to minimize cost, maximize revenue, maximize profit. So just be sure that you do look at that in terms of figuring out like how to find those relative extremas as they relate to cost and so on. Another concept that you may appreciate, for example, is let's say like you were trying to build a oil pipeline that goes from let's say like this point right here, of which maybe this is 8 miles offshore, and then let's say that you have an oil like you have a petroleum company of which that you need to get the oil from here to here, but you don't want to waste money. So in that case, you want to figure out for example if this right here was let's see 8. Okay, so maybe this is I don't know, 16 miles. Then that means that you would have to model it in this sense that how are you going to make the cheapest oil pipeline? Well, you would have to say that that's going to be X, and then this is going to be 16 minus X. So what that means is that to create the cheapest pipeline, you would have to go from here. Let me do that again. You'd have to go from here to here, and then you would just create the pipeline along the shore. So in that case, you could come up with the cost of how much will it cost to build this pipeline. Like let's say for example that you know that underwater it costs 12 million or so. I don't know. Maybe we'll just say 5 million. So then it would be 5 million times that diagonal, which is just the square root of x squared plus 64. And then let's say that onshore it costs maybe like 2 million dollars. So that would be plus 2 million multiplied by 16 minus x. So c of x is in millions in this case, and x is in miles. So this would actually give you the equation that determines the cost of an oil pipeline that goes underwater and also onshore. But in this case, you're not trying to maximize it because why would you? You're actually trying to minimize the cost. So why don't you take a look at this example and try to see like, can you figure out like where the costs are decreasing and increasing because in that case that's going to give you the minimum cost in this case. This is just an example, so if it comes out nasty, that's because I didn't think it out. But this is exactly a classic problem from applications of first derivatives.